So, hello, welcome everyone. My name is Lisa Stewart, Chief Administrative Officer at the Kavli Institute for Theoretical Physics in Santa Barbara, California. It's my honor to welcome you to a talk by Nico Cooper, who will be presenting the 8th talk in the National Society of Black Physicists Innovate Seminar Series, hosted here by KITP. You can find all prior talks in this series posted on both the NSBP and KITP websites in case you missed any of them or are inspired to watch again. The talk itself today will be approximately 30 minutes and presented in webinar format. We will hold questions until the end. So as questions may arise for you throughout the talk, please go ahead and enter those real time into the Q&A section, and following the talk, our speaker will try to address your questions. Next, I'd like to introduce you to Farah Simpson, the leader of NSBP's Student Council, the group responsible for creating and leading the Innovate Seminar Series. Thank you.
Hello, everyone, and welcome back to the NSBP Innovate Seminar Series. We are very excited for this particular one because it is the speaker is one of the Student Council members, Nico Cooper, who is also one of the organizers of the Innovate Seminar Series. The Innovate Seminar Series was created by the Student Council in order to give a platform to our NSBP members so that they could share their research ideas and projects in a non-specialist way with a wide audience. As Lisa mentioned, it's a 30-minute talk followed by 15 minutes of Q&A. We are very excited to have you and to continue holding this space for our members, and we hope that you enjoy this talk. I would like to now introduce the President of the National Society of Black Physicists, Dr. Stefan Alexander.
Thank you so much, Lisa and Farah. Can everyone hear me? Okay,
yes, we can hear you.
Okay, and can everyone see me? All right, so it's a real honor. This is a special one for me personally because Nico is really one of our shining stars in NSBP land. I mean, he is a leader, he is a scholar, he is someone that I just know I look forward. I just have this, this dream that, one day Nico will be presenting his PhD dissertation and there'll be some breakthrough there and I'll be sitting there in the back of the room with my gray hair, enjoying every moment of it. So just a quick introduction to Nico. Nico Cooper is a recent graduate of Princeton University and currently a graduate student in math at Northwestern, in the Chicago area. His research has focused broadly on high-energy theoretical physics and superconformal field theories, and he has worked as a Black queer activist in many capacities, recently as a member of the NSBP Student Council. It's a great pleasure to have Nico. Really excited to hear what he has to tell us today. It's all yours, Nico.
All right, thanks, Stefan. So thank you all for having me. So we're going to be talking about some of the work that I did with my advisor at Princeton, Sylvia Pufu, which is on integrated correlators in N=4 SO2N super Yang-Mills theory, which that's a lot, but what it promises is something pretty cool, which is the ability to compute constraints on scattering amplitudes in string theory without really having to know anything about string theory in the first place. So I'll expect that a lot of this might be pretty confusing, but the main takeaway that I want us to focus on will be a particular approach of computing quantities in quantum field theory that can tell us about a particular theory of quantum gravity. Okay. Cool. So before we fully begin, I want to put us in a position of knowing why we'll be computing these integrated correlation functions in the first place. So putting it briefly, we'll be motivated by an enormous field of research known as the anti-de Sitter conformal field theory, or ADS-CFT, correspondence, which is an extremely miraculous relation between certain spacetimes with negative cosmological constant, which is anti-de Sitter space, and quantum theories that obey conformal symmetry. Come on, there we go. So what this means is that we can describe a theory of quantum gravity in d dimensions in the bulk, by a purely quantum theory on its boundary in d-1 dimensions. And in our case, we'll be focusing on the boundary of type 2b string theory in 10 dimensions. This boundary is n equals 4 supersymmetric Yang-Mills theory, which again is a purely quantum theory. And finally, in this little primer, what I want to emphasize is that integrated correlation functions that we'll be computing are of single trace scaling dimension 2 operators in the stress tensor multiplet of the superconformal field theory, which are dual to bulk supergravity amplitudes. Now, that's a lot of stuff to make us theorists happy, but for everyone else, just think of this relationship as analogous to taking a can of something, say my favorite brand of coffee, and reading off the label to get an idea of what's inside the can without having to open it. In this way, by doing just this, you've taken information that lives on a two-dimensional boundary and used it to reconstruct information about the three-dimensional bulk. So where we'll begin is a little bit about path integrals and how integrated correlators are related to them. And then after that, we'll talk about supersymmetry, why we need it, what kinds of theories we'll be talking about that involve it, and the incredible simplifying power that it affords us. Then we'll move into a bit of an exotic area of math called random matrix theory. That's a convenient description for supersymmetric theories of many interacting degrees of freedom. And it'll help us actually compute these integrated correlators. And then finally, we'll briefly discuss the meaning of these results and some reasons to explore this area in the first place. All right, so to start, what are integrated correlators at all? So one of the most important objects in quantum field theory is called the path integral, which is something that we can actually write down, but is in truth very, very strange and a little bit magical even. But this is an infinite dimensional integral over the fields of your theory. This particular object of interest is the partition function, which is a path integral of the exponential of the action of the theory. It's just the most basic statistical description of the theory that we can even write down. Well, what will be useful for us to think about are adding source terms to this action in here, in the argument of the exponential. And these source terms in this general form, like I've written here, with j multiplying phi. And what we can do is take derivatives of the partition function in terms of j, in terms of this thing that defines the source that we're adding into the action, to define a correlation function of the field that multiplies j. Now, if you've never seen this before, you can really just interpret this as a definition, and correlation functions are just the purely statistical correlation between fields in a theory at different space-time points. And because we'll be interested in theories where instead of a j source term, we'll think of massive terms that we can add into the action as the sources for the integrated operators, we'll take derivatives of the log of the partition function with respect to m, with respect to this mass, which give us the integrated correlation functions of the fields multiplying m. And as well, we're interested in other derivatives that'll be able to give us, in particular, 4-point functions rather than just like the 2-point functions that I've written here. And in high energy theory, these quantities have been studied extensively in QFT. They're some of the most important quantities that one can write down. But again, when I refer to correlation functions, this is the same as just the statistical correlation between multiple fields at particular points in space-time. All right, so now we'll start in on talking about supersymmetry. And I'm not going to try to convince everybody that supersymmetry is a real thing or anything like that, but I'm mostly just going to be focusing on why, when you're suddenly starting to talk about supersymmetric theories, things actually get realistic to compute. You can actually start to compute things. So the particular theory that will be the focus is the n equals 4 supersymmetric Yang-Mills theory, which is essentially a generalization of QCD, which is the theory of the strong force. But whereas QCD has a gauge group of SU3, we can talk about this theory in principle for any gauge group. And we'll focus on SO2n, where n is just an arbitrary number that we can take to be arbitrarily large in our computations. And finally, I'll talk about a little bit of what the field content of this theory looks like. Just one vector boson, 6 massless scalars, and 4 massless fermions, where supersymmetry comes in as imposing a symmetry between some of the matter and radiation of this theory, so that they'll look like they're behaving in the same way. But we'll make this theory even more complicated. As mentioned before, we want to think about adding massive terms into this action before we had a theory without any massive fields. But now we'll want to add in massless or massive terms in a certain way that's called the n=2 star mass deformation, where we endow some of the fields of the n=4 theory that we had before with equal masses m. And in our discussion of the path integral formalism, this corresponds to a source term. Remember that J term that we can just add into the action to define correlation functions. And when we take derivatives of the log of the partition function in terms of the mass and set that mass to 0 at the end, we can compute the integrated correlation functions of not the original n=4 theory, or sorry, have it switched around, not the n=2 star theory itself, but the original n=4 theory. So basically we're saying, okay, we have a massive theory or massless theory that's important to us. We'll add mass and then in this computation be able to write down things that are totally independent of the mass and tell us things about the massless theory that we're interested in. So n=2 star super Yang-Mills has a partition function that looks super complicated, which is derived entirely from properties of supersymmetry that allow us to go from an infinite dimensional path integral to a finite dimensional integral over this, with this term here, which is a gauge group dependent function of the mass. This is all due to the work of Vasily Peston in 2012, but you can just kind of take it for what it is and pick up from here to be able to write down the partition function of this supersymmetric theory with the massive terms that we've added in. Okay, now even more complicated. The SUN gauge group is the one that's most exhaustively studied in the literature, but we're going to focus on the case of SO2n, which has this partition function. It's not particularly important that you remember what it looks like, but it's slightly different from the SUN case, and all you really need to know is that it has these functions h. H is defined here, basically just a function that you can put into Mathematica related to the Barnes G function. And they have as an argument the mass in them. So when we take mass derivatives of this, we can get things out of this. So this may be a finite dimensional integral, but it's still, again, obviously really complicated. So our next challenge is to try to actually integrate it and its derivatives. All right. So as if that wasn't complicated enough, this is where a beautiful language, mathematical language called random matrix theory comes in. So being brief about it, we'll discuss the large n and large lambda limit of our theory, where lambda is something called the 't Hooft coupling, and n is the n is the same n as in SO2n. It's the rank of the gauge theory. So what happens when we do this is that the path integral localizes around a classical action. It starts to look like a classical theory, from which the action has a vanishing derivative and allows us to write down the saddle point equation here. And in the large n limit, the variables a become dense, and we can integrate over their density, solved by this equation where the density is rho. So this allows us to write down f, that is the negative log of the partition function, as an integral weighted by the eigenvalue density rho. And now we've rendered it feasibly computable since the density is known from this equation. So I'll quickly zoom back and forth. So we've taken an integral over n different variables a and said, okay, we don't want to integrate over each of those independently, but we want to write down a density that describes all of them and then just integrate over that density. So if we integrate just the second derivative with respect to mass of the f that I had before, then we can compute a formula for the integrated two-point correlator. And for an integrated four-point correlator, we have this form, which again, I'm not holding you all to remembering what all of this looks like. Just notice that the four-point correlator has these Bessel function terms in it. But if we wanted to do a little bit better and go to higher orders in 1 over n, again, we're taking the large n limit, so 1 over n is sort of our perturbative expansion parameter. We'll need to consider this quantity as an expectation value, which can be written in terms of the inverse Laplace transform of what's called the two-body resolvent. Now, again, what does that mean? Why are we doing this? These resolvents are defined in a particular way for SO2n, the gauge group of our theory. And what we can do is compute recursion relations for these resolvents in orders of 1 over n, which were previously not a known thing for, were previously known for the gauge group SUN in the literature, but weren't known for this particular gauge group that we're talking about here, SO2n, which is the main, was the main interest of my thesis, saying, okay, can we actually go in this slightly new direction? So from this recursion relation, what you can do is, again, here we have the Bessel function terms from the two-point correlator, and we can actually compute another term to the next order in 1 over n. So, okay, I'm not going to hold you all to knowing everything about what was going on there at each and every step, but the main takeaway is that this is a very powerful overkill method to be able to compute things in the boundary theory of a quantum theory or a quantum gravity theory in the bulk. Again, that's very overkill for ordinary situations. So let's look at some ordinary situations where this actually has a whole lot of power. So let's look at two similar theories, which are super QCD and super Yang-Mills, both with the gauge group SU2. Again, before we were thinking about a gauge group with rank, just any rank n, but now we're focusing in on a gauge group of SU2, where it should be a little bit simpler. So these theories have one-dimensional integrals for their partition functions, so it's fairly straightforward to compute quantities in a perturbative expansion. So in particular, the quantities that we'll compute are the same derivatives of the log of the partition functions as before. And what we'll be able to do is plot the coefficients for this perturbative expansion. So what we're seeing here are these plots of the, in particular, ratios of the consecutive coefficients of this perturbative expansion for the integrated four-point functions with supersymmetric Yang-Mills theory on the left and supersymmetric QCD on the right. And we'll notice that to high orders, there's a linear relationship of the magnitude of these ratios. Now, why is that important at all? What we'll notice is that this computation is a perturbative expansion in the coupling G to order n, where n is the x-axis here. Now, what this means in relation to Feynman diagrams is that this is equivalent to computing diagrams with a number of loops on the order of n over 2, which for Feynman diagrams, if you're familiar with doing loop computations, even just one loop computations. These quickly get very, very complicated, and if you try to go up to higher loops, 2 or 3 even, you have to come up with incredibly creative ways to reduce the number of diagrams that you're computing. And looking at these plots, you can see that using this method of computing these correlators and supersymmetric theories, what you can do is that you can compute these integrated correlators to arbitrary loops, which again is equivalent to going up to however many millions, billions of individual diagrams these would correspond to. So if one were to say, try to compute these correlators just with Feynman diagram methods, this is a very easy check on those methods, because this can go up to however many loops that you want. And with Feynman diagrams, you can usually go up to, I don't know, maybe 5, being super, super creative about the methods you use to get there. Now, finally, I want to summarize what we've been able to do. For the SO2N theory, we were able to compute the integrated correlation functions order by order in 1 over n for any value of lambda, the coupling of the theory. So again, these results have some use in their own right, but the big motivating factor that we'll come back to is that they help us constrain quantities in their holographic dual in supergravity, where it's generally very, very difficult to compute higher order quantities. Right, and for the SU2 case, where we again went back down to a bit of a simpler case where we can use this overkill method to do something really, really powerful, these techniques allowed us to compute integrated correlators to high loops in perturbation theory, which can always serve as a check of the traditional perturbative methods. And finally, what I want to emphasize is that these results follow closely the previous work for the SUN gauge group, but the relations to compute integrated correlators to higher orders in 1 over n were not known before at all for SO2n. And the hope is that these relations can be computed in general as they have for SUN, so that we can go up to even higher orders, which can correspond to even higher orders in the supergravity bulk for scattering amplitudes. So yeah, that is where I'll end it. Do we have any questions in the chat?
Yes, so feel free to type your questions in the Q&A chat, and then I will moderate those questions.
Yeah, these can be questions about really, really particular things, but also this was, this went through a whole bunch of different stuff, so you can also just ask really big picture questions that that are as general as you want.
Unless everything was super clear and everyone understands everything.
Come on, even I don't understand everything.
Okay, so we have one question. You showed 2 plots where there was a significant difference for small n. Why are the results different for small n?
Yeah, let me go back to these. Yes. The answer that I can give is that okay, where I'll start is that these correspond to lower loop computations, say the Feynman diagrams, and you can sort of see what's happening, that it's sort of spiking up and down. at these lower orders. So you can tell that there are some divergences that would have to be regulated in these computations. And essentially to get away from these divergences to higher orders, you have to go to higher orders to see this more well-defined behavior for the perturbative expansion. Yeah, and I mean, that's sort of a testament to the power of this method, that, say, computing this particular correlator, there's some weird stuff that goes on to the lower orders. But for this particular supersymmetric theory, we can do this to, you know, as high order as we want. And it starts becoming more well-behaved.
Thank you for your question. And okay, says thank you. Are there any more questions for Nico?
Farah, this is Lisa. I'm not able to type into the Q&A as a co-host, but I'm always curious what inspired people in their careers in academia, especially in science, as a non-scientist. So if Nico would address that question, I would appreciate it.
Yeah, absolutely. I think I've come to realize that an easy way to describe it is that I love a challenge. And I guess the way that manifests itself is that, I mean, I'll go back to it, like, yeah, I mean, all the stuff about random matrix theory is really, really complicated. And while I was reading up on it, it really didn't, you know, it sort of took a while to come back around into what I was actually computing and why it was actually important for what I was doing. So I think that challenge of, you know, diving deep into some incredibly abstract field of math that turns out to be incredibly useful is a feeling that I really, really enjoy. That I enjoy, you know, saying, okay, why am I doing this? And then coming back and realizing, oh, this is actually, you know, really, really complicated, but because it's really complicated, it's also very, very powerful.
Thank you.
And I remember you telling us about some other fun facts about random matrix theory and applications. Would you mind speaking on that? Because that was my favorite fun fact.
Yeah. So, I mean, random matrix theory shows up anywhere that you can describe something in terms of a very large number of interacting degrees of freedom. You know, and that shows up everywhere in life. But one of my favorite examples is that it describes very, very well the time between bus arrivals in Cuernavaca, Mexico, because there is not it's essentially that drivers are doing it, that the drivers are making up the routes on their own, and it's sort of done on the fly. And it turns out that this extremely chaotic system with, you know, people making stuff up on the fly can be described really, really well by this really abstract mathematical language. So yeah, that's another motivator, that, you know, you learn this really, really complicated thing, and you know, it's complicated and difficult, but then you realize once you've learned it, oh, this can be applied pretty much everywhere.
Okay, and I'll just ask one more time if there are any more questions before we close out. Any last minute questions? Okay, thank you so much, Nico. Thank you so much for this amazing talk. I loved learning more about your research. I always hear you and Stefan talking, but never know what you're actually talking about. This was great, especially as I mentioned, Nico is actually one of the organizers for Innovate Seminar Series, so he was on the other side of things this time. I want to thank everyone at KITP and everyone for all our audience members for showing up and supporting our Innovate Seminar Series, and we really look forward to seeing you at our next one.